Hello to all my dear friends. Once again, welcome to this channel Gate Wallah, and I am your friend Aishwarya Sharma, Civil Wallah. So, dear, we are discussing one short series, and today the topic is slab. Okay, in last class we have seen the provisions of torsion, and before that we have seen bond. Since it is one short series, so in one shot we are going to complete entire topic. And today's topic I would like to keep from gate point of view. Okay, obviously all the topics are going from gate point of view only. So today as well, if you will see the syllabus of slab, and then you will be seeing the type of questions which are usually asked in gate. First of all, its weightage is very less, but still what all are the important things which could be asked in gate. So we will be keeping our prime focus in that only. Okay, dear. So welcome once again in this gate one short series, and topic is slab. Yes. So what are the agendas today? So IS code provisions, very important. Relatively I am saying, overall if you consider slab, it is not that important, but in slab if something can come, then that is IS code provisions. Or what could else come? Definitions of one-way slab and two-way slab. You are not going to design a slab questions of one-way slab and two-way slab in your objective exams. Okay, so we will be discussing majorly today the various codal provisions used for slabs. Okay, basically there are two types of slab: one-way slab and two-way slab. One-way slab is like your beam. Okay, because in one-way slab only one dimension is critical, and in another dimension you can apply the distribution bars. But in two-way slabs both the dimensions are critical, both the reinforcement in both the directions are calculated based on their corresponding bending moment. And obviously in two-way slab as well as in one-way slab, shorter side is critical. Okay, shorter side is critical, because if you are going to see the amount of bending for a same deflection, then it is more along the shorter side. So it is going to be more critical. So we will be providing our primary reinforcement in that direction. Okay, we will talk on that later onward as well. Okay, so now IS code provisions. So in IS code provisions, basically we are going to discuss four things. What are those? First, how to calculate the effective span for one-way slab, then or you can say in beam, then what are the various deflection criterias. After that, what are the slenderness limit, or you can say lateral restraint limits. Okay, and after that what is the requirement of steel in slab as well as in one-way beam. Okay, beam, one-way slab, or in two-way slab. Okay, so let's start with effective span. So most of the homework I have already done for you guys. Okay, because I don't want to waste time in this recorded lecture by writing each and every stuff. So whatever could be the possibility, so that I am going to write here already, either in the form of presentation or with the help of marker. Okay, so before the starting of this lecture I used to spend around 15 to 20 minutes in writing only, because there are some things which you would be feeling better in writing form rather than in PPT form. Okay, so first is effective span here. So effective span, there are total 4 cases. Case number 1 is simply supported beam, or you can say simply supported one-way slab. Case number 2 is your continuous beam, or you can say continuous one-way slab. Case number 3 is could be your cantilever beam, and case number 4 can be frames. So if we are talking about the simply supported slab or beam, then in that case you can see, if D is the effective depth and W is the width of the support and L0 is the clear span, and if L0 is the clear span, in that case here we can say that effective length or effective span of the beam is given by either L0 plus D or L0 plus W, minimum of these two, Okay, L0 plus D or L naught plus W, minimum of these two. The next case comes out, L naught is clear span. What is clear span? Which you can clearly see, or you can say the distance between the supports is known as clear span. W is width of the support. Okay. Case number 2, it is slightly confusing, so understand it very carefully. It is continuous beam, or you can say continuous one-way slab. Okay. Continuity can be like this. Both the sides are continuous. One side is discontinuous and one is continuous, and one side is continuous and one side is fixed. So based on that, there are total 3 cases. So case number A, case number B, case number C. If one side is fixed and one continuous, or both the sides are continuous, in that case L effective is given by L naught. L effective is given by L naught, means for A slab and for B slab, okay, whenever I am saying slab, it means one way slab. For A slab and for B slab, L effective is L naught only. But my dear friends, for C category of slab, again 2 sub cases are there. First sub case is when width of the support is less than L naught by 12. Another is when width of the support is greater than L naught by 12. If width of the support is less than equal to L naught by 12, in that case L effective is minimum of L naught plus D or L naught plus W. You can see it is same as case number 1. It is same as in case number 1. But if width of the support is greater than L naught by 12, in that case L effective is minimum of L naught plus D by 2 or L naught plus W by 2. I hope you are getting it. Okay. So once again I am repeating, for A and B, L effective is L naught only, but for C span, what is going to happen? There are 2 sub cases. First sub case, if width of the support is less than L naught by 12, in that case L effective is minimum of L naught plus D and L naught plus W. Okay, same as we have calculated in case 1, case A. And if width of this support is greater than L naught by 12, in that case L effective is minimum of L naught plus D by 2 and L naught plus W by 2, isn't it? Okay. Next case is cantilever beam, or you can say cantilever slab. So here the L effective is L naught plus D by 2. It is L naught plus D by 2. And similarly, this is a cantilever beam or slab. When one end is fixed, another is free. But there are also cantilever of this type, when one end is continuous and another is free. In that case L effective is given by L naught plus W by 2. It is very easy to remember. Here only option is D, so L naught plus D by 2. Here only option is okay, here both options are there, but whenever width is available, we will be calculating L effective as L naught plus W by 2. Okay. And the last case comes out of frame, and in frame the L effective is simply given by center to center distance. Suppose we have a frame here like this, and I want to calculate the L effective here. So it is given by center to center distance. Okay, it is given by center to center distance. That's all. That is L effective. That is L effective. Okay. So there can be question from this particular zone here. Okay, isn't it? Next, deflection. This is also important here, dear. So deflection is the second aspect of IS code provision. Third one is slenderness ratio, and fourth is about some percentage of steel reinforcement. Okay, and all. So there are total 3 things mentioned in the IS code. Okay, the first 1 and 2 are related to the deflection with respect to cast-in level. So it is written here that if we want to calculate the final deflection due to all types of load, which is going to include the effect of temperature, creep, shrinkage, and they are measured from the cast level, okay, of the support of floor, roof and all other horizontal member, it should not be normally exceed span by 250. It should not be normally exceed span by 250. My dear friend, the final deflection, okay, see, the total deflection is going to be in 2 stages. Let's suppose this is your cast in level. Let's suppose this is your cast in level. Okay, before the pouring of concrete, the shattering was at this level, and let's suppose this is the support. So when after pouring of concrete and all, okay, it is going to deflect like this. Okay, and after some long term effects would be there, means the effect of you can say erection of partitions, creep, shrinkage, temperature and all, which is mentioned in the point number 2. So that is a further increment in these deflections. So let's say the immediate deflections here, let's say it is delta 1, and the deflection component after the erection of partitions, floor finishes, okay, temperature, creep, etc. and all is delta 2. So the final deflection due to each and every kind of load, the final deflection due to all loads, which includes temperature, creep, shrinkage, okay, means delta 1 plus delta 2. Delta 1 plus delta 2 is delta. It is delta 1 plus delta 2, and this is equal to what? Final deflection. It is known as what? Final deflection. So this delta 1 plus delta 2, it cannot exceed, it should not exceed, or it must not exceed L by 250. It must not exceed L by 250. Okay, it must not exceed L by 250. Okay, next is, if we are going to check deflection, this yellow one deflection, if we want to check the deflection, okay, which is going to consider the effect of temperature, shrinkage, creep, okay, means occurring after the erection of partitions. So this is this green one is the deflection which is due to the immediate load. What all are immediate load? Immediate load is weight of the above structure, weight of the partitioning, floor finishing and all. So after the erection of partitions, finishing of floors, or whatever is the finishing required above your roof or floor level, after that whatever deflection is coming here, that is due to the long term effect, that is due to the effect of temperature, shrinkage, creep, etc. So it is saying that this long term deflection or afterward deflection delta 2, it should not exceed this delta 2, it should not exceed span by 350 or 20 mm, whichever is less. So delta 1 plus delta 2, it should be less than span by 250, and delta 2 should be less than L by span by 350 or 20 mm, whichever is minimum. Okay, now how to control the deflection? How to control the deflection as per IS code? So for different categories of deflection, for different categories of deflection for beams, we do have different clauses. Like if we are talking, if we want to control deflection in cantilever beam, simply supported beam, continuous beam, or you can say in cantilever one way slab, simply supported one way slab, or continuous one way slab, in that case to control deflections, these all values are given to us. Okay, 7, 20 and 26. My dear friend, we all have studied the strength of material, slope, deflection there as well as structures as well. We know that deflections are inversely proportional to constraints. If we are going to apply more constraint, then lesser deflection would be there. Are you agreeing to me or not? Tell me. In cantilever beam, restraints are available but only on one side, other side is free from restraint. So on the application of load, deflection is more. Okay. Similarly, if we are talking about simply supported beam, then with respect to cantilever beam, the holdness is more there, so deflection is relatively less. But when it comes to continuous beam or fixed beam like that, in that scenario, my dear friend, deflection is further less. Are you getting it? So one thing is sure, if more deflection would be there, then you need a deeper section. If the value of deflection is less, then the thinner section is also going to work for you. You can check it out with any formula of strength of material. Suppose if I want to know what is the deflection due to point load in simply supported beam or at the center of the simply supported beam due to the load which is acting at center. So it is W L cube upon 48 EI. If I want to know what is the end deflection in cantilever beam due to a end point load, it is PL cube upon or WL cube upon 3 EI. So one thing is sure, deflection is inversely proportional to Young's modulus as well as moment of inertia. So moment of inertia, if it is increasing, then deflection is automatically decreasing. Okay. So to control deflection, we need to fix the depth. More depth means more deflection. Oh sorry, more depth means more moment of inertia, and more moment of inertia means lesser deflection. So as you know that what it is given there, so the vertical deflection limit shall assume to be satisfied for one way slab and beam if basic value of span to effective depth shall be, means span over effective depth shall be, let me call it A. Let's suppose these 7, 20 and 26 are A values. So if you want to check out for effective depth, then effective depth would be span over A. So from now only, from common sense only, you can identify that if A would be lesser, requirement of depth would be more. And we all know cantilever is very much prominent for deflection. So the value of A must be less for cantilever. Relatively simply supported beam is having a lesser deflection. So relatively the value of A for simply supported beam, you can say more here, and again relatively continuous beam is going to have the least deflection, therefore the value of continuous beam is highest here. Okay. So why it is 7, 20, 26, again I will say this is experimental, but the logic behind this order I can tell you. Further thing, all these span, these A values are valid up to 10 meter, but if span is going to exceed 10 meter, then we need to revise this value. We need to revise this value. Okay, cantilever value cannot be revised because IS code doesn't recommend any span in cantilever format which is greater than 10 meter. But yes, simply supported beam and continuous beam can be enhanced. Simply supported beam and continuous beam, these can be enhanced. Okay, so what is that modification factor? So modification factor for simply supported and continuous slab, or beam is equal to 10 over span. Here you need to insert span in meters, 10 over span. Okay, 10 over span. Suppose if I want to calculate the requirement of depth for simply supported beam for 12 meter span, then it would be 12 over 20, and this 20 would be multiplied by 10 over 12. 12 over 20, 20 is a value of simply supported beam, multiplied by 20 over 10 over 12. Okay. But again this 10 over span modification is not available for cantilever beam because code doesn't allow any beam or slab greater than 10 meter span in cantilever format due to its excessive deflection. Just imagine if you are providing a cantilever beam of let's suppose 5 meter, okay, let's suppose 4.9 meter, okay, just for simplifying our calculation. Then for 4.9 meter span, what is the requirement of depth? It is 700 mm. Span over 7 means 4.9, 4900 upon 7, and it is 700 mm. So 5 meter span requires 700 mm depth. Just imagine if it would have been a 9.8, then it is 1.44 meter deep section is required. That too effective. Still you have to provide covers. So overall section would be around for a 10 meter span, overall depth of the section required would be around 1.5 meter. So it is going to create a lot of inertia, okay, lot of dead load. So that is the reason why code is not going for cantilever greater than 10 meter. Okay, even I know this this 10 meter is also on paper. On reality, I am quite sure nobody is going beyond 4-5 meters. Okay, okay dear. Now next here, so not only this modification factor, so let me write it here. This modification factor, it is not for cantilever. Indirectly code wants to say that cantilever beam is not allowed beyond, it is not allowed beyond 10 meter of the span. Okay. Next is, apart from these modification factor, there are certain more modification factor which based on the percentage of tensile reinforcement. Like you can see that it is from IS code. One thing important I have discussed earlier as well, whatever are these photos, I would like to keep these photos directly from the IS code. Okay, are you getting it or not? So reference is IS code, all these photographs are from IS code. So that is the reason why I don't even change the font and all. Don't think I am lazy, I cannot make all these things. Obviously I don't have to make, operators have to make, but still just to give you the perfect sense, I try to keep even the font as well, because they are snapshots of the IS code book. Okay, so whenever you will be revising your IS codes, then yes, by watching this figure your that page would be revised, I am quite sure. Okay, so percentage tension reinforcement is this, and based on that modification factor you can read. Okay. Similarly, if values can be enhanced based on percentage of tensile reinforcement, then obviously if your beam is subjected or slab is subjected with compression reinforcement, then based on that as well your values are going to improve. So this is MF2. Okay, the earlier one was MF1. Okay, this we are not considering. This is applicable only if value of span is greater than 10 meter. Okay, and one more thing there, for flanged section, we do have a reduction factor. Can you guess why? Why do we have reduction factor for flanged section? So you can see based on the ratio of web width to the flange width, we do have a reduction factor. If ratio is 1 means no reduction, so it is 1 only, but for any other ratio this value is going to be less than that. You know why? Because again the answer is in basics only. We know that deflections are inversely proportional to moment of inertia. In flanged section, okay, so no doubt the flange width are more. So based on that we cannot say that entire width is having entire depth is having a constant width b. So due to the non availability of area in the middle zone or in the bottom zone, the moment of inertia value decreases because of the lesser availability of the mass or area. So if moment of inertia is decreasing, then we cannot overestimate that. So in order to keep it as it is, we need to think that moment of inertia value has been decreased, means deflection is more. Deflection more means a value has to be reduced. Okay, so what is the consequences of in flange section? Moment of inertia is lesser, and what is the result of that consequence? That deflection is going to be more. So how I am going to compensate that consequence, that outcome? By decreasing the value of modification, by decreasing the value of A. If A value will be decreased, then automatically requirement of D would be increased. Okay, so that is the case here. Okay, So these are consecutive figure, figure number 4, 5 and 6. Okay, I think it is available in the page 38 and 39. Okay, one figure is in 38 and remaining two figures are in 39. Okay dear, and for two-way slab dear, and for two-way slab, these values are given. Okay, for two-way slab the shorter span up to 3.5 meter with mild steel reinforcement, the span to overall depth ratio given below may be assumed to be satisfied if vertical deflection limits of loading class up to 3 kPa is 35 and 40. Okay, this is for mild steel, this is for mild steel. And if it is for HYSD steel, so it would be how much? It would be 28 and it would be 32, because it is written here for HYSD bars the value would be multiplied by 0.8, or you can say it is 80%. Okay, so these are the deflections requirement. But yes, remember one more thing, it is the overall depth. So span over overall depth is B value, span over overall depth is B value, isn't it? Okay, let's proceed further. Now dear, slenderness limit, it is again important that to ensure the lateral stability. Why we need to ensure lateral stability? So that load should not come out of syllabus. You know, we are preparing for vertical loading and all, but it can also buckling can also happen in lateral direction. So just to make it safe, we need to ensure that the distance between the support should not be greater than some particular value. Okay, so that is known as the slenderness limit. And in case of continuous or simply supported beam, that limit is going to be same, because simply supported beam as well we are going to calculate the distance between two consecutive support, and in continuous beam as well we are going to calculate the distance between these two support. So what is going to happen here? What is going to happen here dear? So in simply supported beam, or you can say in continuous beam, the distance between the support is going to be how much? It is minimum of 16b or 250 b square by d. Okay, where d is effective depth. It is 60b or 250 b square by d. Okay, but yes, when it comes to cantilever beam, then what is actually happening there? In cantilever beam, it is not about the distance between the support, because we do have only one support. So it's all about the unsupported length. So the maximum unsupported length which is allowed in the cantilever beam is how much? It is again minimum of 25b and 100 b square by d. It is 25b and 100 b square by d. Okay, so just to explain these points, let me show you a small example. Suppose we do have a cantilever type span whose span is 8 meter and whose size is 300 by 600. Okay, so the span is 8 meter and whose size is 300 by 600. Now if I want to check lateral stability and deflection criteria, so how I am going to check? So for deflection criteria, what we can find that requirement of depth is span over A. So no modification factor is required here, because the span is less than 10 meter. Anyway, it is also a case of cantilever beam. So here the span is 8000 meter and 8000 mm and value is this. So it is 1 4 something. Okay, so let's suppose it is 1 1. Let's suppose 4 3. Okay, so you can see that I hope it is coming out this only 1 okay, around 1143 mm, it's alright. So anyway, it is coming greater than 600 mm. So we have provided 600 mm and the requirement is coming out to be of 1143 mm. So it is failing in deflection criteria. It is failing in deflection criteria. It is failing in deflection criteria. Now let me check it for slenderness criteria. So maximum unsupported length is the minimum of 25b or 100b square by d. So in this case 25b is coming out to be 7.5 meters. Okay, b is 300, so 7500, and it is 900 upon 600. Okay, so 9 upon 6. I think it is coming out to be, where is my phone? Just a minute. Okay, so it is coming out to be 100 300 square divided by, it is coming out to be 15 meter. It is coming out to be 15 meter. Okay, let me also check that as well. Now I have taken calculator. 1142.8. It is 1142.8. It is 1142.8. Okay, so that only 1143 only. Okay, so here they are saying that this is going to be the minimum of these two, means cantilever beam, for a cantilever beam and for this size I cannot provide a beam whose I cannot provide a length whose unsupported length is greater than 7.5 meter. This is what it says. And what size I have taken? I have taken it 8 meter. So it is also failing in slenderness ratio, as the rule says it cannot exceed 7.5 mm, but we have provided 8 meter. Okay, from here you can take an assignment. What you can do, you can simply, instead of cantilever beam, take simply supported beam and check for these corrections. Okay, and check for these two checks. Okay, dear. Now dear, after that, the requirement of steel reinforcement. What is the requirement of steel reinforcement? In the beams, the minimum tension reinforcement is given by 0.85 into BD upon Fy. Okay, it is 0.85 BD upon Fy. Okay, so where AST is the minimum reinforcement, BD is the effective cross section, 0.85 upon Fy is the yield strength of the steel, and it is minimum one. And maximum tension reinforcement cannot exceed 4% of the total cross sectional area. 4% of the total cross section area, both maximum tension and compression. Minimum compression, obviously it is 0 because it is not required many of a time. Sometimes it required. So minimum even can be 0, but minimum tension we have to keep it this one. Okay, and the reason behind this minimum reinforcement is this: there should not be a snipping failure. So we make sure that each and every cross section is going to have at least this much amount of steel. Okay. So next is for slab. If we are working with mild steel, then 0.15% of the total cross section, or if we are working with HYSD steel, then 0.12% of the total cross section. Okay, and when it comes to diameter, the diameter cannot exceed thickness of the 1/8 of the thickness of slab. 1/8 of the thickness of slab. Okay, for example, if slab thickness is you can say 75, if slab thickness is 75 mm, in that case what is the maximum diameter? Diameter should not be greater than 75 by 8. 75 by 8 is slightly less than 10, it is 9 point something, and we cannot exceed that 9 point something. So what is the best available diameter for us is, obviously we cannot go for 10 because it cannot exceed that 9 point something. So we have to go with 8 mm diameter. Okay, so like this we can conclude. Okay, now when it comes to maximum spacing, then for main bars these maximum spacing is a minimum of 3D or 300 mm, and for distribution bar it is minimum of 5D or 450 mm. Okay, it is minimum of 3D or 300 mm, and for distribution bars it is 5D and 450 mm. Okay. Now nominal cover. What is nominal cover? Nominal cover is the nominal cover, I hope you know what is that. It is the design depth of concrete cover which is going to cover the all types of steel reinforcement including the links. For example, let me show you here that suppose I do have a beam here like this. Suppose I do have a beam like this. Okay, and let's suppose again we do have some steel stirrups here. Sorry. Okay, so let's suppose we do have a steel stirrups here like this. Okay, and let's suppose there are some reinforcement. Okay, okay, and one more is there. Let's suppose that all are of same size. What is happening here? Okay, so what is effective nominal cover? Nominal cover is measured from the outer of this. It is measured from the outer of this to this. This is known as nominal cover. It is known as nominal cover. Okay, it is known as nominal cover. And what about effective cover? Effective cover is measured from here. This is known as effective cover. This is known as effective cover. So here the provisions of nominal covers are given. Depending upon the exposure condition, different values has been suggested, and these different conditions are mild, moderate, severe, very severe and extreme. For mild conditions at least we need to go with the 20 mm nominal cover. Then for moderate condition it is 30 mm, then for severe it is 45, very severe it is 50, and for extreme conditions at least we need to provide nominal coverage of the order of 75. And similarly some minimum grade of concrete is also suggested by code, that for mild condition we can go with M20, for moderate condition we can go with M25, for severe condition we can proceed with M20 or more, and for very severe condition we can proceed with M35, and for extreme condition at least we need to provide M40. Okay, so this is the case here. Okay, and yes, now dear, when it comes to design of beam or you can say one-way slab, okay, I hope you know how to differentiate between one-way slab and two-way slab. Okay, so one-way slab is basically that slab where the prime bending moment is happening along the shorter side, and longer side need not to be designed. We can only provide the distribution bars based on the minimum percentage of steel requirement, like what we studied, 0.15% for HYSD bar and 0.12% for what? It was for HYSD bar and 0.15% for mild steel. Okay. So all these are the coefficients. First of all, you need to target that which span or which panel you are going to design. So these all are the coefficients if you are going to design end panel. These are the coefficients for intermediate panel, and these are the coefficients for shear forces, and these are the coefficients for bending moment. Here the coefficients for dead load and live load are different. Okay. Similarly, the coefficients in shear as well are different for dead load and live load. Okay. So center one, the one which I have shown with the positive sign, they all are the beam moments, and the negative one, they all are the support moments. Once the value of bending moment is known to you and shear force is known to you, so rest of the design is similar as in case of a beam. Okay. So these all are the design steps for one way slab. First of all, calculation of load, then bending moment for shorter span. How we can calculate the bending moment for shorter span? It is if it is a case of simply supported beam or cantilever beam, then simply we can add dead load and live load, and maximum bending moment would be WL square by 2, WL square by 2, like that. But if it is a case of end panel or intermediate panel, then first of all we need to segregate between the fixed load and live load, and we have to multiply fixed load and live load with their corresponding coefficients with the length square. Okay. That we can read from that Cordell provisions coefficients. Okay dear. Then the rest of the procedure is same. Then based on the maximum value of bending moment, you can calculate the depth of the slab, then you can calculate the area of the steel for shorter span, then you can along longer span you can distribute the mild steel or HYSD steel. You know how to give the spacing. Okay, it is for distribution bar it is 5D or 450 mm. Okay, then we can apply the checks for bond, shear, okay, anchorage, etc. Okay, so all such checks can be done. Okay, let me tell you one more time that why shorter is critical. Suppose if this is a slab, you must know this, and here are deflections. The same deflection, the same amount of deflection you are going to face here as well. So this and that the deflection are same, obviously same beam, so same deflection. When it comes to their curvature, so it is going to have a circle like this, but when you are going to see this curvature, so it is going to be like this. So you can see that this radius is very less, so curvature is very more here, and that radius is very high and curvature is less here as compared to this curvature. And we know that bending is inversely proportional to radius of curvature, or it is directly proportional to curvature. Okay, so obviously the shorter span is critical in one way as well as in two way. But one difference is there between one way and two way, that in one way the other direction need not to be designed, we can simply provide the distribution bars, but in two way slab the other directions are also need to be designed. Okay, it depends upon the span ratio whether you are going to say your beam as one way slab or two way slab. If all the four sides are supported, and the span ratio is greater than 2, in that case you can say that your slab is one way slab. If all the four sides are supported and your span ratio Ly over Lx, if it is greater than 2, then you can say your slab is one way slab. Okay, because in that case the other side becomes, longer side becomes insignificant when it compares to the shorter side. So that's why it is known as one way slab, means designing is only going to happen in one way only. Okay, and remember one more thing, that if only two opposite sides are supported, then irrespective of the span ratio, a slab is always one way, because if only two opposite edges are supported, then irrespective of the span ratio it is always going to show you deflection only in one direction. Okay, but yes, two way slab is that slab when all the four sides are supported, so span is known as two way, if its span ratio is less than 2, like 4 cross 3, okay, 5 cross 4, okay, in fact 5 cross 3 as well, yes, 5 cross 3 as well. So such span are known as two-way slab. Means both the sides bending moments are comparable, means both the sides curvatures are comparable. It should not happen that one curvature is very high and another curvature is very low. It should not happen. Okay, if we would be having a span like this, if we would be having a span like this, dear, let's suppose rectangle type, okay, let's suppose it is 4 and let's suppose it is 3.5, it is 4 and 3.5. Now you see that this curvature and that curvature are almost comparable, so we need to give significance to both of the bending moments. So we need to provide area of steel as per the exact value of bending moment. Okay, so such spans are known as two-way slabs. Okay, dear. Now other than calculation of bending moment in both the direction, each and everything in one-way slab and two-way slab are same. Okay, but yes, there are some ways by which we can find these bending moment in both the direction. I am not going into the detail of these, but yes, you should know the name if you are preparing for some exams like of JEE or A11. So the various methods here are Rankine-Grashof theory, Pigeon's method, Marcus method, and IS code method. IS code method is universal. It is universal. It is going to cover all possibilities of two-way slab. Okay, this Rankine-Grashof theory is like is used for your two-dimension simply supported beam, and when corners of the beams are allowed to lift up. Okay, and this Pigeon method and Marcus method, these are also the advanced method over Rankine-Grashof theory. In fact, Marcus is the advanced method of Rankine-Grashof theory, but here the end are restrained partially. Okay, but IS code method is the complete solution. Okay, if you want to study something on two-way slab, then you can study about Annexure-D, page number 90, 91 I think of IS code. You can study that Annexure-D. Okay, so IS code method is going to give you complete solution. Not much I am telling, but yes, in IS code method you have to calculate bending moment in x and y direction based on alpha x w lx square, based on alpha y w lx square. It is also lx here in my as well. So how alpha x alpha y can be read? It can be read by the span ratio versus coefficients ratio. Once mx and my are known to you, then remaining thing you can easily calculate. Rest of the procedure is same. For mx calculate astx, for my calculate asty. Provide asty in the along the longer side, relatively longer side, and provide astx along the shorter span. Okay, so it's like that. Okay, so why I said that it is the universal method? Because it is going to cover all the possibilities. Means whatever possibility is there, okay, suppose we do have here like this. If you are studying to the table, so let's suppose all these ends are fixed, all these ends are restrained. So doesn't matter if it is interiormost panel, you can look at the row number 1 coefficients. If one short side is continuous, if one long side is discontinuous, sorry, if two adjacent sides are discontinuous, then this is the case. Okay, also cases may be like this: two shorts are discontinuous, two longs are discontinuous. Okay, so any possibility can be there. Okay, So any possibility can be there. 3 sides are discontinuous. Okay, 3 sides are discontinuous. Okay, all the 4 sides are discontinuous. So all the possibilities covered there. All the possibilities are covered in IS code method. Okay, so calculate the moment as per the annexure D. Then check out the condition that which table you have to use for using the value for reading the value of alpha x and alpha y. After that, repeat the same story. Yes, some more torsional provisions are there, that how to provide the torsional reinforcement as per an XRD. Okay, when there is a requirement of providing torsional reinforcement, when both the 2 adjacent sides are discontinuous, in that case you need to provide the torsional reinforcement. It has to be provided in 4 layers. Okay, and first of all you have to make a mesh of Lx by 5 by Lx by 5, and in that max you have to provide 3/4 of AST provided in 4 layer. Okay, if one side is continuous and one is discontinuous, then you have to provide 3/8 of AST in 4 layers, and if both the sides are continuous, then no need to provide torsion reinforcement. Okay, so just have a look in IS code, you will be knowing, because all the things are theoretical there. Okay, so just you have to read that by your own dear. Okay, what is important in this chapter from gate point of view? You should know how to calculate the effective span. You should know the deflection criteria very well. You should know how to check for slenderness limit. You should know what is the minimum maximum percentage of steel in beam, slab, compression, what is the minimum value of nominal cover, allowed value of nominal cover, particular value grade. Okay, design coefficients value no need to by heart. If by chance any question comes in gate, then they will give you coefficients, so no worry for that. Okay, you should know the basic definitions, difference between the one-way slab and two-way slab, that is really important to note there. Okay dear. Okay, if apart from that, if you want to study something, then you can study IS code method from annexure T. Outline I have given, and exact clauses you can see once. Okay dear. So thanks a lot. So let's keep the session only up to here. So next session I will be taking on, after slab, column. Next session I will be taking on column, and that lecture you will be watching on Monday. Okay, bye bye. Thank you.